Good morning everyone. So for today, I would like to the last chapter for our subject, support vector machine, SVM. So in this particular video, talk about history. What machine is, a bit about the SVM technology, and later on we will talk about types of SVM, whereby we will have several types of that, non-linear and linear. We will discuss how SVM works, and then we will talk about margin for SVM, soft margin for SVM2, and later on we will focus on this for non-linear data, and particularly how the non-linear data work and the application of the kernel function. Then a discussion of the disadvantage of support vector machine is happening, I guess, in the nearly to the end of this slide. And we will talk about the application of SVM. Before we end the lecture session, basically we will how to implement the SVM, especially by using the Python. Okay, so utilizing the cancer data. So I'll showing up several types of Python example codes available publicly from GitHub. Okay, right, let's get started. Okay, to begin with, basically we will try to take the concept of machine learning before this. So we have three categories of machine learning. If you guys still remember from the beginning of the class, we got a supervised one, the second unsupervised, while the last is reinforced. Okay, so here the idea of supervised is classification, the one that we did discuss, and regression. Okay, so this one happened to be discussed whereby using regress is linear, if you guys still remember, and logistic, and this one is a class A and B, kind of is simple. And for unsupervised, I think we did discuss about PCA over here. Okay, so then this one is still not discussing yet because this is not the coverage of the our subject. Okay, and for the supervised learning, as we did discuss before, so we have regression and classification, right? So the regress means the things that related to the trend, if you guys can remember about that trend. So meaning we give something and we will predict something in a trend. Okay, so it could be linear or quadratic line. Okay, so then we will talk about classification is separating the data, whereby let's say we have this data, so we kind of separate these two. Okay, so over here we will consider this one is a group A and the other one is group B. Okay, that would be classification, right? In this particular videos, basically we will talk about this, the capability of SVM in order to do this. Okay, right? So in history, basically SVM was invented by a Russian mathematician Vladimir, if I pronounce it correctly, in mid 1960. Okay, it's all about 63 years ago. So then immediate after that, I think 30 years afterwards, the idea was extended in somehow for regards to the network, kind of. Okay, so the SVM uses the different types of loss function over here. Okay, and learning algorithm compared to a neural network. So it is unique, utilizing unique error landscape minimum, so no need for iterative algorithm. So the iteration happen in an end. Meanwhile, in this particular SVM, it wouldn't require to have a training session, means again and again and again, right? So can solve the linear and non-linear both by separatable to separate the problems which are given. So yes, okay, now what is the support vector machine is? So normally in the normal perspective of machine learning context, so we can see easily that we have SVM topics that has been discussed widely. So SVM is that support vector machine. So a set of supervised. So it is lies on the supervised learning methods, whereby it could do classification, do regression, and do outlier detection. So that would be kind of interesting thing about SVM. So not to mention about the advantages of SVM, there are several. Effective in high dimensional spaces compared to the regression. Then in that particular time, still effective in cases where number of dimension is greater than the number of sample. Okay, so that would be the advantage. SVM produce significant accuracy with less computational power. So whereby obviously as we mentioned earlier, iteration reduce. So that would be the advantage of the SVM. It can solve linear and non-linear both problems and work well for many practical problems. So it is one example for the outlier things over here. So this one is classification. Okay, so whereby here we have kind of interesting to be discussed over here. So whereby we call this as a kernel. Okay, later on we will talk about that. KER, sorry. So the kernel means to have a solution for, let's say we have x and y, two-dimensional. Okay. So in the logistic regression, in the regression basically we try to use the multivariate regression, right? So apart from here, basically we will separate the data by switching this dimension from 2-dimension into 3D dimension, guys. Okay, so whereby we will split the data in this parts and that part. So by using the kernel. So this one is the kernel. Okay, regarding to SVM terminologies, a bit about that. So support vector machine stated that the data point that are closest to the hyperplane. So, okay, so support vector whereby the data in the training is basically considered as the closest one. So for instance, for the cross data, basically we have two. So this one is the support one, and this one is support one, and this one is this one. Okay, so this one is the support vectors that call it, separating line with the defined with the help of data points of this vector. Okay, for this vector, so hyperlane are the that define the hyperlane are the support vector. So meaning this one is another important thing in SVM. They call it hyperlane. Okay, a decision plane or space which is divided between a set of objects having the different classes. So this line basically separating to this the data given by dividing them into one set of class and this one set of class. So that would be two separating, or what we call it, hyperlane in this particular SVM terminology. Okay, right. So margin is the gap between the lines, okay, between two lines of the closest dataset point of every classes. Okay, so margin is this. Okay, so gap between two lines of the closest data points of the difference. Okay, this is meaning this will be the gap and this also will be the gap, guys. Okay, it can be calculated as a perpendicular distance from the line to the support vector machine, or kind of this one and this one to this one, right? So large margin is considered, okay, this one is the most important. Large margin is considered as a good margin and small margin is considered as a bad margin. Okay, so let's say we have this one, we have that, so we have this one, we have that. So the large margin is preferable or better than small margin. Okay, so in this context, so that would be three terminologies on the SVM subtopic, whereby we need to confirm and understand about the support vector. What is support vector? There will be 1, 2, 3. Hyperlane is this line. Margin is the line, the gap between these two lines with the hyperlane. Okay, by looking up to the location of support vector. Right. So now we jump to the types of SVM. So we got two types of SVM then here. So one is the linear and the other one is non-linear. Okay, by its name, linear, I think most of us as engineer know this is linear. So non-linear, that one and that one. Okay, it happened to be non-linear line, we could say. So linear SVM is used for linear separable data. So whereby if I make use over here, so we can separate them. Sorry, it's not straight line though. So we can see this one is the most farthest, right? This and that. Okay, so the most far from the line. Okay, two classes by using a straight line. So consider this one is the straight line. Then such data is termed is linear separatable and classified in use called as linear SVM classifier. So this one is linear SVM classifier. Okay, while in opposite, we have non-linear support vector machine. Non-linear SVM is used for non-linear separated data, which means that if the data cannot be classified by using the straight line, so we kind of hard to separate these two lines, right? Because there would be a separated data whereby the data was scattered in the middle. So which means if target cannot be classified by using straight line, then okay, right here, non-linear data and classify use the what we call it non-linear SVM classifier. So it could be this. Okay, so just now I mentioned about the kernel. So this would be happen afterwards. So by fusing a kernel concept to the 2D data in order to separate the two groups of data. Later on, we discuss we will discuss it in details. Okay, how SVM works, right? So we did discuss about two terminologies in the previous slide. One is support vector, the other one is margin, the other one is one more is hyperlink, right? So hard margin. So hard margin for SVM, find the boundary with maximum margin. So meaning the support vector with the line is basically having the most maximum length. Okay, so what we call it maximum margin. While the soft margin SVM is whereby we originally it's kind of not getting to the difference between this, but the slack is basically the data has been added, or it is could be considered as outlier of that particular data. So we can say we still consider as it is as outlier for this particular group. Okay, so that would be soft margin in order to get the margin for SVM. And kernel trick, okay, to solve the non-linear problem. So this one is I mentioned earlier. So by having a kernel kind of things, it could be this space, it could be like this in 3D, it could be like sigmod thing, is it? Okay, this one is in 3D, guys. So imagine that this is 3D things. Okay, so the 3D needed to be used over here is when we might difficult to separate it two kind of data. So that's what we call it. We change the XY, looking up the XY by adding Z kernel. So meaning by using the Z kernel, so the high of this data is different by using this kernel. So meaning the dot data is basically lower than this hyperplane, while the cross data is upper than hyperplane. So we will talk about that afterwards. Okay, hard margin SVM. Okay, so in hard margin SVM for linear separatable, so this case for the linear one, separatable data. So we can take a look over here. This one is hyperplane. Okay, So this one is obviously margin because this one is support vector, this one is support vector. So this would be the same length as it is. So this is the margin one for red group, and this one is the blue group margin. Okay, so that would be the margin separated the data into each classes, right? Okay, so margin between the classes. Okay, so defining the margin between the classes, the criterion that SVM seek to optimize. Okay, so this one is the optimized one to be considered as SVM. So the goal over here is to maximize the margin between the point on the either side of the decision line. So as an example, we can see over here several possible. Okay, so the keyword is several possible decision boundary. So it might not be considered as only one, so it could be considered as two, guys, or three. Okay, whereby we still have the maximum SVM margin, okay, for that particular context. So again, the maximum margin hyperplane shows that the greater the distance, the more confident that the sample belongs to the class. Okay, so why is the greater distance over here stated? That if we have the greater distance between support vector and hyperplane, okay, then the statement comes in the more confident that the sample belonging to the class. So meaning to say that if we have the more distance or margin, so meaning this one is the training data, guys, train data. So let's say in the future, basically we brought a new data, let's say here or here. So we can easily say that this X belonging to the class B, while this dot is considering as class A. So because the separation between the two classes is clear and the margin is big, huge distance, so now the model can easily guess so the target classes for the new cases. So whereby this one and this one is a new cases, guys, this and that. So while in this middle one is being considered as our training data before we use the models in order to predict which one is the data belonging to, okay, in class, right? So in the same way as the one that we predict in regress, whereby we have the line in regress, right? So we have the data here. Okay, in regress, basically we find the line, right? So then again, we pull a new one to the line. Let's say this is the x-axis for this particular data, right? This one is the test data. So all we need to do is basically find the y prediction. So that is the same concept as referring the linear and referring the model. So happen also in neural network, the one that we did discuss last week. Okay, so the keyword over here is the wider margin, the better SVM that we have, right? Okay, so good margin and bad margin in our vision perspective, we could say that the good margin having as far as possible for the both sides. So this one is the keyword. Okay, both side means this and this. So this one is side A, example, this one is side B. So the length over here is as far as possible, right? The things, the margin. Okay, the bad margin is whereby although we have a good marginal for the side A, but for the side B, the side B is struggling because the hyperlane that decide the decision line is very close. The margin is too small. So that's what we call it not a good margin. Okay, and we could say also the bad margin over here. Okay, so again, then we said a good margin is one where this separation is larger for the both cases. Okay, so the good is for the both classes. Okay, not a single, not for only one class, but for both classes. So meaning up and down. Okay. Okay, right. So we did talk about soft margin over there, and now we will talk about the soft margin for SVM over here. Okay. So soft margin, flexible SVM models for outlier data. Okay, right. So this one is the hard margin one. Hard margin cases, we can say that the margin is kind of wider. Okay. So for instance, this one, either we couldn't get, okay, let's say in this one is A case, this one is B case, right? So say that happen we have this point and this point, so we pull this line, okay, as a decision boundary for our SVM hyperplane, right? So then we should consider that where is our support vectors. Okay, so the support vector in this particular slide, whereby we represent it as a circle for this. Okay, so this one is support vector. This support vector SV. So while this one to support vector, this one too. Okay, so sample violating constraint. So it doesn't mean that this is the violating this concept. Okay, this one and this one, because of the every data has the hole in the middle of that particular point. Okay, we have the white circle in the middle, so this one and that one, right? Okay, so this outlier is still because of this range or margin is still small, so basically we could consider as it is outlier data point. Okay, so the similar thing that I did mention in the first 3 slides before. Okay, so considering that one is the outlier, it's not the true requires data for our target, right? Okay, SVM for the nonlinear. So until here, until up to the page 12 from page 1, so we did talk about linear SVM. Okay, so meaning from this beginning up to this slide. Okay, so from the slide number 13, basically this one is 13, we will consider that the SVM is non-linear, guys. Okay, non-linear data. So SVM uses I mentioned earlier, kernel. So yeah, kernel, it could be varies in some depending on the sum function that we have. Later on we'll talk about that. So the SVM uses kernel function. So the kernel function is this, whereby we could consider that this one is the function reflected to a new plane, instead of this one is x, right? This one is y. So we add one more, z. So this particular separating group is considered as plane. So that's the reason why you can see over here the rectangular shape kind of kernel is shaded by a gray color. So that would be considered as gray. Okay, so this is happening over here. So in this perspective, two-dimension perspective, having us to be 3D perspective, so all the blue data will going down, as I mentioned earlier. So because respected to the z plane, so this one is xz, if we take a look here, it will be mapped until one certain point. So whereby this red cross is mapped to the upper side of that particular point. So this line is referred to this height, the hyperplane, whereby we can see in, let's say I put it this way. So imagine this is x and y. So you can see from the side. So this one is a z. So the hyperplane is this, guys. The line. So the dot is here. If you can see by side, so this one is x, guys. So we can separate them by having this kernel. Okay. Imagine that you see from the side. Okay. Right. So what we call here is kernel trick. So the kernel function. Okay. So the kernel over here is a function projected the data into higher dimensional. Okay. Higher dimensional feature space means if we have two-dimensional 2D feature in our hand, so higher mean 3D lah. See? So makes it possible to perform a linear separation. Okay? So this kernel will be considered as a linear separation. Okay? But by adding one more dimensional. So that would be SVM kernel. Okay? So how SVM for nonlinear data works? Okay, this is the step-by-step slide to show us how we're gonna have the clear picture of this data. Okay, as I mentioned earlier, we have this one for our preliminary data that we have in hands. So we have the circle kind of blue data over here. Okay, so and then we have the middle point of a black data. Okay, black dot data. Okay, all right. So this is no line that can be separated the two classes in X, Y. So let's say I would give you this line. It is impossible, this line or this line or that line, right? So each of the four lines is basically impossible for this particular thing. Okay. So then the idea is when we try to put the kernel trick over here, we apply transformation and add one more. Okay, so add one more dimensional, as we call it z-axis. Okay, so now image this is y. Okay, this is y, this is x. Okay? So x, y. Let's say this is x. Okay, so this x and y. So basically this graph is turning to this space, so becoming y over here, x over here. So then we can see that the separation happen when we add the z. Okay, so as I mentioned earlier, the here, remember the one that I put it this way. So x is this high and z is that high. So similar to this one. So basically the x, the black dot is happen to be referred to the z, the new dimension, as a z at that particular height of z axis. Okay, so then we can say that the blue one is higher in z plane. Okay, so then we can say that this one is a kernel, whereby the kernel is separating those data in new dimension. So that would be kernel function purpose. Okay, so this one is, sorry, okay, so this one is basically the kernel, guys. Okay, so then after we can see that the data is separated physically from the middle to the rounded data that we have over here, so black and blue. So now we turn back those 3 dimension into the 2 dimension back, so as a number 3. Okay, So we transfer back to the line. So then we have this separation after applying the kernel trick. Okay, so we know that this data is separatable by using the kernel trick after we put it 3D back to 2D. Okay, so then this is D1. Okay, so I provide here a picture of dividing gen X, for example, and gen Y. Okay, okay. So obviously the data is mixed around. So as we can see over here, similar as this, right? Over here. So what we gain here, we cannot put it this line, that line, that line, and that line to separate two classes over here, meaning cancer and normal person, right? So to do this, we pull this 2D into 3D because of the kernel is adding one more dimensional for that particular 2D, right? So the same thing happened. This is X and that dimension is Y and this dimension is Z. Okay. So then we plot it again. So basically this blue is having the value of below of this kernel value in Z. Okay. While this rectangle, the square data, red data, is basically beyond this kernel. So then again, the slicing of that particular thing over here below the dots is this. Okay, so that would be the thing. Okay. Okay, kernel function is various in several contexts. So this is the example of kernel function. We do have a radial basis function, or we do have Gaussian. So the quotient is this, for example. So the linear one happened to be discussed earlier in the previous slide. Okay. And obviously linear is two classes. Okay. Polynomial means this, while sigmoid is this, guys. Sigmoid, I think we did cover in linear regression before. The things that having this function, right? Okay, so polynomial means could be anything. Okay, it depends on how we do it. So Gaussian is this function, Gauss. So but it applies in 3D. So that would be happening for splitting this data using this kind of Gaussian cap. Okay, so the data whereby located at the top of this Gaussian is considered as one group, whereby the data is below the Gaussian kernel is considered as this group, right? So that would be kernel. Okay, so the kernel using k, x1 and x2 for the two-dimensional for the two classes data, right? Okay, so this one is SVM for nonlinear. We do have the nonlinear cases for sepal length. So do you still remember about this data? This data has been discussed before as iris data, guys. So the flower data sets. Okay, so with the linear kernel, we can't see that the this particular 5 types of flower which available in iris could be separatable. Okay, or we can see 3. Imagine that this is 3 types. Okay, non-separable because it is mixed around. So to do that, we try to use linear kernel. So this one is normal linear kernel for SVC. So still cannot be. So this one is RBF, radial basis function, or what we call it Gaussian. Still, I think is quite okay compared to this one. So because this is one group, guys, right? So this one is one group kind of. but we have the intersecting group in this white thing. Okay, so then again, if we reduce the degree of 3 for the polynomial, basically we could see this and group of the white dotted. Okay, even though it will be overlapped with the red dotted one. So that would be kind of interesting, having better kernel function compared to this. This one is less, this one is less than this one is less than this. So meaning this will be okay one. Okay. Although the SVM is good in certain contexts on the supervised learning, so it is not cannot avoid the disadvantage of the cases demands of the training. Okay, so somehow it is not suitable for large data sets. Okay, it is quite okay for intermediate or the middle data sets amount of number. Does not perform well when the data sets has more noise. Okay, so whereby the target classes are overlapped. So whereby this is happening here. Okay, so this is not very kind of good, but it's still performing. In case that where the number of feature for each data point exceed the number of training data sets, just that the SVM will be underperformed. Okay, so that would be one case for giving the disadvantages of the SVM. Okay, we need to be careful about that. Okay, so these are the application for SVM. We can see the face detection, classification of the images, text and categories, bioinformation, handwriting detection, remote homology detection, and generalized predictive control. So face detection, it could be like face, many faces, data. So you want to split it to two categories kind of, and things. Okay, text is the minis data. So the idea of 1, 2 until 0, right? Data sets of images. Bioinformatic is thumbprint. Okay, and so on. So normally we can see over here the implementation of SVM is having 5 steps to go. So I think cross over all the approach of the machine learning having the same idea of this step. So first thing first is loading the data, exploring the data, because we want to check the data, is it rather the data is available or a blank. Okay, so that will be happening especially in your assignment last 2 weeks time. Okay, and then we should split them. Example, train and test, we must have 80% or 20%, or some stored say that 70% or 30%. Okay, it depends. And after we split the data, we try to generate the model using the library and package prepared by the open source. Okay, so we pull the library in our codes, and then we generate the models. So then the model again will be used. This is example XX. Okay, then we give one data as X, so we can predict the Y using the model evaluation, right? So the model trained in step 4. Okay, so this is the idea whereby we use the example of using Python. This is the loading data step. So I think this is importing the sklearn. Okay, because of data set is basically taken from here. Okay, so we give the name for this data set. So the data set is coming from here by the sklearn. So datasets package has the command for load. Okay, and breast cancer for data bringing in, and this data basically will be read as cancer underscore data in our program from this line to the below one. Okay, So we print it and we can see that the data for 0 until 4, okay, 5 layers lah. Okay, then we try to explore. Obviously the cancer data is the things that we declared just now. So target is here and data shape is this. Okay, so that would be the idea. Target means 0 classes, guys. So target, we can say that 0 or 1. So in this context, maybe it could be normal and cancer. Okay, that would be the thing. So whereby there will be 2 classes for this sake of application. Okay, use case in Python. Okay. Step 3, we split the data. Obviously, we pull the library from sklearn, model selection over here. Okay, so the command here that we brought is train, test, and split. Okay, in order to split the test and train. So this is the cancer data. Again, we I think, hold on. Okay, so it repeats. So somehow it is not required if you write down from step 1, step 2. So this is not necessary to rewrite again. Okay. So the important things that to be wrote here is x train, x test, y train, y test. Obviously, this one is for training. This one is for testing. Okay. So train, test, split means this coding will be how to say, will be standardized for all the SVM dots all over the world to split either 70 or 30, right? It depends. Okay, so okay, you can set them. Okay, test size is this. So meaning 40%. Render state is, yeah, you can randomize them. So this one is target. Target meaning 01 tadi, 01. Okay, generating the model. Okay, now, so from sklearn, SVM has been imported. Okay, so this one is a code whereby from this particular line we use SVM dot something something. Okay, so this one is declaring the kernel linear, whereby the kernel just now we have RBF, we have sigmoid, we have what sort of thing, many. So then we feed the data after we train it, and this code is okay. This code is basically the prediction. Okay, so then we try to elevate them by precision recall, and this one is the accuracy for the training. So this one is 96.4%. That's it in percentage. Okay, so that would be the case of having a good SVM training over there. And here is the other Python example from GitHub. You can take a look. So GitHub is basically the, how to say, the place that whereby all the contributors around the world are pushing the codes over here. You can easily get the data, get the Python code. Let's say this one, for having the vector machine or random forest or KNN. Okay, so you can take a look. And this one is the example using sklearn too. So dataset, model, and matrix. So this is the one that we have. Also, you can how to say? Okay, matplot, import matplotlib is the package whereby it works for representation. Okay, plot. So rather than others is taking here, taking there, it's not a big deal. So yes, so this one is splitting one, and this one is importing the SVC from sklearn SVM. So fit, classify. Okay, don't forget this one is new declaration. This one is parameter, param. Okay, so SVC is this because of we call this one into here. Okay, prediction is the same way as before. So because of the classifier is SVC, So we just put it here. So prediction in total is basically classifier dot predict. Okay, so this one is X test. So we will have the Y test value over here. Okay. So this one is coefficient matrix, whereby let's say this one is 0, 0 and 0, 1. So let's say 0, this one is actual, this one is predict. So say that the picture is supposed to be target 0 and predict to 0. So meaning the 0 test image has been has been predicted as 13 out of 15 images are correct predicted. Okay, so the only 2 is missing for 0. So meanwhile the 3 is missing, but this one is true. So obviously it's still good lah, 83%. Okay, so plot decision 1 is here. Okay, this one is for linear one. Okay, hold on. This one is linear, if I would say. So this one is non-linear, guys. This one classifier means, hold on. Okay, the kernel is RBF. So meaning the kernel is this. Okay. So there we can say, we can see that the, okay, so this is 96%. Okay. This one is 83% kernel poly. And when we use sigmoid, 76%. So you can see, even though SVM itself pulling the different types of kernel, so we can see that the sigmoid kernel is 36%, poly is 83%, meanwhile the RBF is 96%. So obviously RBF is defeating all the 3, so win. Okay, so whereby for this particular data, so we should use the RBF instead of the kernel 3 degree, meaning x3 line. I don't know this one. Okay, thanks. So this one is sigmoid meaning the one that we have just now. Okay, okay, so that would be the thing. So yes, there will be more references to be referred in this one, in this lane. So I think that's all for the SVM in this video. I hope that you guys can rewatch the video and see you guys in the next video. Bye. Thank you. Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.